Okay, so good morning to the people who are present. Am I audible and the screen is visible? Can Aryan or Koli Bhavna, can you confirm?
Yes, sir.
Okay. So we would start. Thank you, yes. So we were doing basically jointly Gaussian random variables in our last lecture, in lecture 22. We did that. This is very much important because if you need to study, let us say if we model the noise in the communication system as a white Gaussian process, then you have several operations which you would be doing on the received data. So we must know that by what means the properties of those noises will change once they pass through some filters. Okay, let us say they pass through band pass filters or they pass through low pass filters, then what will happen to that noise? In order to know that, we need to study these jointly Gaussian random variables. So we were at this point of uncorrelatedness. Okay, I think let me start with this, that we said that joint Gaussian density, if we have a vector, let us say x, which is x1, x2 up to xm, where each of the element is Gaussian distributed, then for x to be a jointly Gaussian random vector, their linear combination needs to give you a Gaussian random variable for all possible combinations. Now suppose if that is satisfied, then can we define the density of x? So for that, we must note that it should not be that one of the random variables can be expressed in terms of others. Okay, it means that the density should have a m-dimensional representation. It should not have an m-1 or m-2 representation. Where we did one example here where we said that let us say there is a random variable x1 and there is another random variable x2 which is obtained through some affine transformation over x1. Okay, we showed that x1 x2 would be jointly Gaussian, but density won't exist because knowing x1 you can completely say what value x2 would take. Okay, so on the two-dimensional plane this is simply like a line. Okay, so we didn't go deeper into that because we thought that for our purpose we must know that one of the random variables should not be simply obtained from the other one. It means ऐसा नहीं है कि हम बोलेंगे they need to be uncorrelated. No, they can be correlated, but the relationship should not be deterministic. Okay, so if at all that is the case, then we can define the density of x like this, and the expression is given by this. Okay, that we see that there is an inverse of the covariance matrix. So we need covariance matrix to be a full rank. If it is not a full rank, then you cannot take the inverse. Inverse doesn't exist. So full rank means that there should not be a deterministic relationship among the rows or something. It means if at all you try to do some row operations over C, one of the rows should not be a linear combination of the others. I think this you may remember from the earlier mathematics courses done during the first year. Then we thought of expressing uncorrelatedness. We said that if the covariance is 0, then they are uncorrelated, and if at all the variables are jointly Gaussian, then they are independent as well. Okay, so there is an important result that is called an exception to this rule, that independent random variables are uncorrelated, but converse is not true. But what is the exception? Exception is in the case of jointly Gaussian random variables. So exception means that if they are uncorrelated, they would be independent. Okay. So at this point, we closed our session. Today we would move ahead. Today we would discuss somewhat white noise in deep and Gaussian random process. And from next class, we would start with the match filter. Finally, from the next class, we will be doing the last component of the course, presumably that we have to study several modulation schemes and their detectors. Okay, we have built sound base, I think, by today. Towards the end of the class, we have sound base. From next class, we will do all the statistics. So I think continuing from where I left, so let us say we have to obtain the variance of a sum of random variables, variance of a sum of random variables. Suppose you need to obtain that. So this is like this, variance of x1 plus x2. Let us say we are trying to obtain the variance for small m number of random variables. This is same as saying that this is the covariance of x of m comma x1 plus x2 plus xn. Okay, that is covariance of the variable with itself, that will give you the variance. This is simply nothing but summation. There will be two summations. Okay, I am not deriving this. This is very straightforward to see. If still any doubt persists, you can just contact me. I will help you out with this. This is merely a small algebraic operation which you will do over this. That is, you write the covariance formula and then you can obtain this. Okay, which can be further written as summation of I is equal to 1 to m variance of xi plus summation of I is equal to 1 to m I not equal to j covariance of xi comma xj. Okay. Now, why we are doing this is we will be showing that if the variables are uncorrelated, then the sum of the variance, the variance of the sum would be the sum of the variances of the individual random variables. Okay. This is what we want to show. So, for uncorrelated random variables pairwise. So, we are writing pair. That is important to specify. Pairwise, that is every possible pair. This must be remembered that we are saying that it is valid for every possible pair. The variance of the sum, equals the sum of the variances. Okay, so because if we are saying that they are uncorrelated, so these terms would be 0. So all of them would be 0. So you will get that the variance of x1 plus x2 plus, let's say, xm is nothing but the summation of the individual variances. This is an important result which we may use at whenever you do the statistics for studying the detector. We might use this directly. So I just shown you that this is the way we basically understand it, or this is the way we derive it. Okay. Now, one important thing which you can see from this is, so you can say that this is some sort of a corollary, or you can say a result which is based on this is, now if, let us write, now if x1, x2 up to xm are pairwise uncorrelated, and now we assume that they are jointly Gaussian. Okay, so what happens? So assume that they are pairwise uncorrelated. Let us say for any xi and xj, where I and j run over 1 to n, you basically obtain the covariance, all the possible covariance, that is covariance of xi comma xj. If all of them are 0 except for I equal to j. Okay, this should be remembered, because if I is equal to j, then this is covariance of xi with xi. That will give you the variance of xi. That won't be 0. Okay, if it is 0, then it's not random. So are pairwise uncorrelated and jointly Gaussian. Now suppose they are jointly Gaussian. Then C is a diagonal matrix. Okay. Now what does this mean? Diagonal matrix. Why? Because let us see where we defined our C. Okay. So this is C. This is the covariance matrix. I think we must have defined it at some place. Yeah, this is C of phi, which is variance of this. Okay. Let me see where we have done it more properly. Okay, I have not written it in terms of, I think here we have defined it, but we have not written it very specifically. Yeah, here you can see that the I and jth element of the covariance matrix would be given by this. Now we have shown that for I not equal to j, this would be 0. Okay, why? Because they are, okay, let me just first of all complete it and then we can go back. Okay. C is a diagonal matrix, and the joint density matrix and the joint density, and let me first write and then we will go back and explain, so that we have the explanation together. Decomposes into a Product of marginal density. See, this is very important. Product of marginal density. So this proves that if at all your variables are uncorrelated and they are jointly Gaussian, so they would be independent. Okay. Basically, these are few results which you must basically remember. So they are asked in a lot of places, even if you may try to make a research career in industry or in academia. These are very, very basic interview questions that if at all you are given a pair of Gaussian random variables which are jointly Gaussian and they are uncorrelated, what can you say about them being independent? So you would say because they are Gaussian, they would definitely be independent, but this may not be true for other possible probability distributions. So let us go back to what I was explaining. So this was the covariance. So you know that if at all xi is uncorrelated with xj, this whole quantity is zero. Okay, that has to be. That is what I think we have shown here. Let me just revise it for you. So this is what we wrote, that if at all xi and xj are uncorrelated, so their covariance is zero. Now what happens when I is equal to j? Let us go back. Okay. Here. So if I is equal to j, this is expected value of xi square minus the square of its mean. This is nothing but the variance of xi. And when I is equal to j, all these values will appear on the diagonal. Why? Because I is equal to j. So diagonal elements are those where the row number and column number are same. So except the diagonals, all other elements would be 0 if at all xi and xj are pairwise uncorrelated for all I and j except I is equal to j. Okay. So this means this would be a diagonal matrix. Now once this is a diagonal matrix, if I try to substitute a diagonal matrix in this expression, you just see what is this expression. So let us revise one thing, that if at all you are given a matrix, we will take a 3 by 3 example. So this is 3, 0, 0, 0, 2, 0, 0, 0, 4 suppose. This is A. And I say that try to find out A inverse. So A inverse is nothing but you just take the inverse of each of the diagonal entries. So this is, I think, a simple way of doing for the diagonal matrix. Now that will be the case. Now if at all there is a vector, suppose I am defining one x, which is nothing but x1, x2, x3. Okay, and I try to obtain x transpose A inverse x. What would it be? So let us do it. So you will see that this is nothing but sum of elements. Okay, let us do it. So this is x1, x2, x3, 1 by 3, 0, 0, 0, 1 by 2, 0, 0, 0, 1 by 4. Okay, and you do x, x1, x2, x3. Now remember that this is in exponential. Okay, so this is equal to 1 by 3 x1, then 1 by 2 x2, and then this is 1 by 4 x3. Okay, and you have this x1, x2, x3. So this is nothing but equal to 1 by 3 x1 square plus 1 by 4, sorry, 1 by 2 x2 square plus 1 by 4 x3 square. Okay. Now you know, if I go back and see what is the density, so this is in the exponential minus 1 by 2. So let us see. So if I do it exponential minus 1 by 2, this sum 1 by 3 x1 square plus 1 by 2 x2 square plus 1 by 4 x3 square. This can be very well easily written as minus 1 by 6 x1 square into exponential minus 1 by 4 x2 square into exponential minus of 1 by 8 x3 square. Okay, so this has basically disintegrated into three terms. Now let us check the initial term here, what it would be. Okay, this is 1 upon root of 2 pi to the power of m. So 1 upon root of 2 pi to the power of m is 3 in our case, and determinant of the covariance matrix. It is not, I think, the inverse, it is simply the determinant of C. So determinant of for a diagonal matrix is simply product of the diagonal elements. So it is 24. Okay. Or I can write it like this as well. 1 upon root of 2 pi 3 into, let us say you write the three elements, 3 into 2 into 6, 3 into 2 into 4. So this can be written as 1 upon root of 2 pi cube, or I can write it to be like this. One upon 2 pi to the power of 3 by 2 into 3 into 2 into 4 into this product. Let us say this is A. So this can be written as 1 upon 2 pi to the power of 1 by 2 into 3, 1 upon 2 pi to the power of 1 by 2 into 2 into 1 upon 2 pi to the power of 1 by 2 into 4. Now just combine each of the exponentials with each of the terms. You will get that this is a product of, like this, it is exponential. Let me write it down. Basically, I am doing it in an easy manner, so things are clear to most of you. Into 3 into e raised to power minus of x2 square by 4 divided by root of 2 pi into 2 into e raised to power minus of x3 square by 8 divided by root of 2 pi into 4. Okay. Now what it is basically? This is expression for a normal. This is the density for a normal, zero mean, and you can calculate the variance, whatever it would be. Similarly, this would be also zero mean, and you can calculate the variance, the normal, zero mean. Okay. But this has basically is the joint density is now the product of individual densities. Now this is one of the primary requirements if at all you need to say that x1, x2, x3 are independent. So this is what is now proved. So this proves that if at all they are pairwise and correlated and jointly Gaussian, it means they admit a density. Then jointly Gaussian and, sorry, may not admit a density, but we have taken a case where they have a density and then they would be independent only, because their joint density can be written as product of marginal densities. Okay. So obviously this is valid if at all the density exists, or it should not be the case that one of the random variables can be deterministically written in terms of the other random variable. Okay, then they cannot be called as independent. They cannot be. Okay, and I don't think that they would be uncorrelated also. They would be fully correlated. So in that case, it doesn't apply. Okay, so this is what I wanted to say. Now the last thing which we need to ponder over is the joint Gaussianity under affine transformation. What happens to the random jointly Gaussian random vector once it passes through some system? Okay, joint Gaussianity under affine transformation. Okay, so this is important for us to understand that if x denoted as x1, x2 up to xm is a Gaussian random vector, this now you must be very clear that when do we call a vector as Gaussian random vector, it should not be that each of the elements are Gaussian, then it is a Gaussian random vector. No, they have to be Gaussian, plus every possible linear combination should give you a Gaussian random variable. This may not be satisfied even if all of them are individually Gaussian. But yes, there is a result that if they are independent, then they would be definitely jointly Gaussian. We are not going into that. If at all we need it later, we will state it at that time only. Okay? Or if at all you are going through the textbooks yourself, let us say during the course, then you can just read and appreciate and understand it yourself, because we may or may not use it. So if x is a Gaussian random vector, then y is equal to ax plus p. So now suppose I do an affine transformation where this is vector, this is matrix, this is matrix. These are two vectors, they are all vectors. Okay. This is also Gaussian. This is a result. This will really help you a lot in later stages. Why? Because there you can simply use this result. So once you can use it, it simply says that you can obtain the density of y in terms of density of x. So you only need the covariance and mean vector of x. So this is the beauty of this result, that you don't need to derive what will be the distribution of y. So I would write it completely. Just give me a moment. To see, so let us see it in simple terms, or you can see intuitively a simpler proof. To see any linear combination, any linear combination of the y's. Okay, let us take y. Now y of n. So remember, this n and m are different. N and m are different. You may have a transformation where you either reduce or increase. Okay. Yes, to see any linear combination of this equals a linear combination of okay, that is quite simple, because let us, if at all I obtain this vector and try to take the linear combinations, then these linear combinations can be easily expressed in terms of linear combinations of these x1, x2, x3. I think this is very clear, because each of y's is a linear combination of x's. Okay, what is y1? Y1 would be the first row of A multiplied by the complete x vector plus the first element of B. That will be y1. Similarly, that will be y2, yn you can obtain. Now, if you take the linear combination of y's, so ultimately you can get a linear combination of, or you will get a linear combination of x1 to xm. Okay, plus a constant, that is important. There will be a constant plus a constant. Okay, which is a, so which would be a, which is a Gaussian random variable by the Gaussianity of, so we assume that x is a Gaussian random vector, so it means, so by the Gaussianity of x. Okay, now if that is the case, it means y would be Gaussian, because x is Gaussian. Since y, now we know that y is Gaussian, so since y is Gaussian, its distribution is completely characterized. Its distribution is completely characterized by its mean vector and covariance matrix. Okay, so if x is normal distributed with mean and variance c, I think this I have already shown you in the last lecture, that how would you obtain the distribution for this. That would be, mean would definitely get changed because of the additive constant, and this will be like this. Okay, so I think we are done with whatever base we had to build. So we will close this with a small example. So this is a small example. Anyways, I will update the lecture breakup file with the sections of the textbooks I am following. I have not yet uploaded the possible questions in them. I will definitely try to do it in a day or so that those who want to practice a few problems from the textbook, they have the problem set with them. So suppose x1 and x2, we have given an example, are jointly Gaussian. So it is given that they are jointly Gaussian. Suppose they are given that they are jointly Gaussian with, so you are given the mean, x1 is 1, expected value of x2 is 2, sorry, minus 2, variance of x1 is equal to 4, and variance of x2 is equal to 1. And the correlation coefficient of x1 and x2 is -1. So these are the details which are given to you. Okay, so first of all, the first exercise is that what is the mean vector? I think that would be easy to obtain. So we have, that is x1 and x2, we stack together. And then what is the mean vector? Mean of x is nothing but the expectation of individual elements. This is a very, very simple example. This is just to basically solidify what we have understood. Then second thing is what will be the covariance matrix. So covariance matrix, the entry 1, 1 is nothing but the variance of x1, which is nothing but 4. Then C of x2, 2 is nothing but variance of x2, which is equal to 1. Now what about C of x1, 2? So this can be easily obtained as rho of x1, x2 into variance of root of variance of x1 into variance of x2. I think this is the formula which you need to go back and see for the correlation coefficient. Correlation coefficient is nothing but the covariance divided by the square root of this. So you multiply, so you will get it. So this is nothing but minus of 1, because this is given, this is -1 into square root of, let us multiply the variances, that is 4 into 1, that is 4, and this comes out to be -2. Now what is the guess about Cx2, 1? That would also be same, because nothing else has changed. That will simply rho of x1, x2, or I think I should write it more properly. This is x2, x1. That is a better way to write it. Under root of variance of x2 into variance of x1. Now this factor is same. This and this are same. What about this? So in the case of, you can say real random variables, they would be same. Okay. I am not going into it. You can do it. That I will write it as homework. That rho of x1, x2. So there is a question mark whether it would be equal to or rho of x2, x1. Okay, so I'm not going into it because this directly depends on the covariance. So I will write. So, or this implies, the question implies another question, that is covariance of, is it equal to covariance of x2, x1? See, the answer to this is that if the random variables are real, then they are equal. And if they are not real, if they are complex, then this is linked by a complex conjugate expression. It means covariance of x1, x2 will be equal to the star of the, or the conjugate of the covariance of x2, x1. Okay, because covariance can come out to be a, you can say, generally covariance should be a number, but that is what happens in the case of complex random variables. Right now, my work or our study is not on complex random variables, so I am not going deep into it. But this is just a question which is written for you to ponder over. But for the real case, it would be equal. So we are right now dealing with the real random variables. So this is equal. This is -1 into root of 4. This is -2. So the covariance matrix now you can easily construct. So G of x is nothing but 4 -2 -2, and this is 1. Okay. Now one small example, that another example from the same question, that what will be the probability of twice of x1 minus thrice of x2 to be less than 6. Okay. So what to do is that let us take a root of joint Gaussianity. So we know that x1 and x2 are jointly Gaussian. So any linear combination is a Gaussian random variable. So this would be a Gaussian random variable. So let us represent this by a Gaussian random variable, which is y. So this is same as probability that y is less than 6, where y would be a Gaussian random variable because x1 and x2 are jointly Gaussian. Okay. I think this should be, this can be easily seen. Okay. So what will be the mean of y? So that is easily you can obtain, that is 2 times mean of x1 minus 3 times mean of x2. So I'm just directly writing down the value. I'm not showing the calculation, it would be easy for you to do. And what will be the variance of y? Variance of y is nothing but the covariance of y with y. What it would be? It would be covariance of twice of x1 minus thrice of x2, comma twice of x1 minus thrice of x2. That would be the covariance. Now if you obtain it, I am just writing directly 4 times covariance of x1 comma x2, sorry, covariance of x1 comma x1. So this is an example from the textbook directly. A well crafted example, I would say, for us to understand the concept well. Minus 6 times covariance of x2 comma x1 plus 9 times covariance of x2 comma x1. There should be one x2 comma x2, let me check. It should be 9, it should be x2. This should be x2. Okay. So this comes out to be 49. So now it becomes an easy task. We need to obtain the probability y is less than 6. This is nothing but the CDF of y, and we know the expression. The direct result is this function. So this would be 6 minus 8 upon root of 49. Now why we have done this? We have shifted y to, so I would write transform to 0, 1. Okay. अभी ये क्या है? This is normal with the mean. What is the mean? We have obtained it is 8 comma variance is 49. Okay. So the way out is subtract the mean and scale it by root of variance. So this comes out to be phi of minus 2 by 7. Okay. And this is nothing but same as you can use a Q function also to obtain the result, that is 2 by 7. So this interplay between this phi and Q we have seen, we have gone through it. So I assume that this should not confuse you basically. Okay. Now one interesting last part of the example. Afterwards we would move to the Gaussian random process. So this example is also very interesting. The part of this example. Let us create another random variable a times x1 minus x2. Okay. So we have created a linear combination. Okay. Let us say we have created a random variable y or z. Now I want to study z and x1 together. What the individual random variables would be, whether they would be jointly Gaussian or not. Okay, that is the point. So to check it, let us take an arbitrary combination. Okay, so arbitrary combination, let us take it to be b1 times z plus b2 times x1. What it would be? That will be a b1 times x1 minus b1 times x2 plus b2 times x1. So ultimately this will be a b1 plus b2 times x1 minus b1 times x2. Okay. Now you see that because x1 and x2 are jointly Gaussian, so any of their linear combination is a Gaussian random. So it means that any linear combination of z and x1 would be a Gaussian random. So this shows that they are jointly Gaussian. Okay, they are jointly Gaussian. Right now we have not imposed any condition on a and b1, b2. They are arbitrary. Okay. Now the question is, what is the question? That find the constant. Find the constant. This is a good question. Okay. A such that now we need to impose a further condition. Z is independent of x1. Now this is very good thing to do. Independent of x1. Now intuitively this question is quite intriguing, I would say. Why? You are saying that I am creating a random variable by taking the linear combination of two random variables. And now I am saying that x and z and x1, because x1 is contributing to z as well, they have to be independent. Can it be the case? you will find that yes, it can be the case, because x2 would put in sufficient randomness that z can become, x2 puts the randomness, but we need to find a such that this becomes independent of x1. Let us find it out. Now we have shown that they are jointly Gaussian. So if at all they are uncorrelated, then they would be independent, because we have seen the result that if random variables are jointly Gaussian and they are uncorrelated, they would be independent. So let us obtain the covariance of z and x1. Okay. So what will be the covariance? Let us obtain it. This is nothing but covariance of a x1 minus x2 comma x1, and this comes out to be covariance of x1 comma x1. So I think, oh sorry, this has to be, I have written the example incorrectly. This has to be like this. Yeah, that's why I was, while explaining, I thought that there is some problem. There has to be a times x2. Okay, so this will be b, a will be removed from here, minus a b1 times x2, it should be. Okay, it has to be a b1 times x2 plus b2 times x1. Okay, so this would be like this. b1 plus b2 times x1 minus a b1 times x2. Okay, because now we have to add, that is what I was explaining, that we have to add sufficient randomness to x1 such that this becomes independent of x1 itself, and we want a measure of this. What would be that? A. So I want to add sufficient randomness to x1 itself such that this becomes independent of x1, and this is possible. Intuitively this is not. You will say that once I know x1, I can say something about z, but that something should be 0 now. It means it becomes completely independent. For it, let us choose the value of a. You will find that there is an answer which exists to this problem. That's why I thought of discussing this example in the class, because this will help you at several other places. So, what will be the ultimate expression? So that would be covariance of x1 comma x1 minus a times covariance of x2 comma x1. I think this is directly from this. So this turns out to be 4 plus 2a. This is the answer. Now, for it to be 0, for covariance of z comma x1 to be 0, a should be equal to minus 2. Okay. So this is what happens, that if at all z is nothing but x1 plus 2 times x2, and you create, so if you check this too, they would be independent. Okay, so this is a very good result, that if you have just added this much of randomness to the variable x1, so x2 is the random variable, so this becomes independent. Okay, so this is what we have to do in it. So let us now come back to the Gaussian random process, because that is ultimately the noise which we will add to our system, or which basically happens in reality, but we would now add to our pulse. Okay, so we have studied the pulse transmission. So let us now start with the Gaussian random process. Okay, this is the process of our interest. Really, basically this we would be using. Now you can see the dilemma of the person who is either teaching this course or studying this course. First of all, we need to know what is a random process. Then we need to know what is a Gaussian variable, random variable. Then we need to know what is a Gaussian random process as a whole. Okay. So the chain of study is, so first you need to know Gaussian random variable. Then you need to know random processes. Then you need to know jointly Gaussian variables. Okay, that is important, because the definition Gaussian variables. Oh, sorry, I should write RVs. Okay. So this will explain that why we have gone through a longer route. And finally, you need to know the Gaussian random process, GRP. So we have now done this, we know this, we know this, we know this. Now we are defining GRP. Now, once I will write the definition of GRP, you will then appreciate that why did we do this. Okay, we invested 2 of our lectures into this. So a random process x of t is said to be Gaussian, if the random variables x1 equal to x of t1, x2 equal to x of t2, that is, you take some capital N instants of time, and at those instant of time you collect the random variables, because this we have seen that in the random process, if at all xt is a random process, so for each time you get a random variable, so you collect those capital N random variables, basically have an n-dimensional Gaussian PDF. For any n, this is important, for any n and any this is basically the star point. Okay. Now that is explains our this chain. First of all, we need to know Gaussian random variables, because x1, x2, xn would be Gaussian random variables. Then we need to know the concept of random process, because time is involved now. Then why jointly Gaussian random variables? Because if at all they are not jointly Gaussian, they cannot have an n-dimensional Gaussian PDF. So it simply means that x1, x2, xn have to be a jointly Gaussian random variables. And if this phenomena happens for all or any n, and for any of the time instants, then that is a Gaussian random process. So just to basically understand this definition, we have to understand all the preliminaries, and those preliminaries will help us in different contexts also. If you go and do some study in image processing, or you go and do some study in even physics and other branches, wherever you can encounter the Gaussian random variable, all of this theory would apply. Okay. So we will directly. So the PDF of this is already discussed. So if I create a vector like this, which is nothing but x1, x2, up to of x of n, which is nothing but x of t1, x of t2, x of tn, then the PDF is already discussed. So the PDF is already known to us, and is given in lecture 22. Okay. That would be a jointly Gaussian PDF. That jointly Gaussian PDF is written in terms of the matrix. Let me just show it again to you. This is the PDF. Okay. So few properties, few very important properties, let us discuss. So few properties. This will really help us. Few properties of Gaussian process. Okay. So one very important property is I have not stated yet, but I have said it several times, but now I am stating it. Okay. Since the xi's, which is defined like this, x of pi, are jointly Gaussian. This we have said that unless it is not a Gaussian process, are jointly Gaussian. The xi equal to x of ti are individually Gaussian. Okay. This I have stated it several times, but I have not, sorry, I have just said it several times, but I have not stated, so I have just written it. Okay. Second property, other properties which we have already discussed, I am not noting it down here, noting them down here. Once you will go back and see the textbook, or if you see the notes in together, then you will realize that we have stated some of the properties elsewhere also. Okay, instead of this common place. A linear transformation, a linear transformation of a set of Gaussian random variables produces another set of Gaussian random variables. Okay, this I think we have done it when we said y is equal to ax plus b. Okay, and this is an important property, a wide sense stationary Gaussian process. What is wide sense stationary? We have discussed it when we started our study of random processes. Is also stationary. Means if at all you say that you have a Gaussian process which is WSS, then you can basically easily say that it would be stationary as well. Okay, stationary, or some books will use it strictly stationary. So you can, I think, juggle between the notation, but the meaning is, when we say it is wide sense stationary, it means few of the conditions for stationarity are relaxed. We are only dealing with one or two conditions. So that's why it is called as wide sense stationary. If we call strictly stationary, then means all the condition for a process to be stationary needs to be satisfied. Okay. Now one very important theorem which we state without proof. Okay, this will help us when we apply a filter to the received signal. Okay, so whenever you apply a filter to the received signal, so noise also passes through that filter. So the question is, if I model noise as a wide Gaussian process or as a Gaussian process, what will happen to the output of that filter? It means the noise which I get at the output of the filter, what will be its statistic? So that is, this theorem tells you. So if the input to a linear system is a Gaussian random process, the system output is also a, so this is a very important theorem. So if at all, see, whenever we apply the filter, so we say that it is a linear operation. Why? Because we will take the convolution of that filter impulse response with the input. That is a linear operation, so that will be a linear system. So the output of that, let us say if there is a noise NT, if I apply at the input of a filter, and that is a linear operation, linear system, so output, the process which I will hit at the output will also be Gaussian. Okay, so this proof not required, but interested reader can refer, interested reader can get it from standard textbooks. Okay, standard textbooks on probability, or you may get it in the books we are referring also. Okay, so this is what is a Gaussian random process. Now we come back basically. So this is what I wanted to introduce for the Gaussian random process, because rest everything we are done with. So one final thing is, let us restudy white noise process. Okay, so few things were pending. I didn't do it that time. I just introduced it. Let me check. I think whether I did it in the last lecture or last to last. I think I must have done. Yeah, last to last I did it. So we just introduced that what would be a white noise, but we need to go back and do a few more things to understand it somewhat deeply. Okay. So first of all, the question. The question is why white? So I would be answering a few questions here. Why called as white? So noise, though we know noise means any unwanted signal or any one unwanted disturbances. Process we know now what is a random process, but why white word is used? While defining white noise, we said that the power spectral density is a flat thing. If I write Sx of f, which is versus f, so this is a flat. It means let us say this is n naught. That is the way we defined it that day. But that is not the standard way to define a white noise process. Okay, so today I will give you the standard way also. So for the initial motivation to the communication engineers, that's why most of the times this definition is somewhat introduced first. You will say that white noise process is a process whose power spectral density is a constant throughout the frequency band, because engineers understand frequency band much better than the classical definitions. Okay. So that is the approach we followed. I just introduced this the engineer's way, but today I will give the classical way also. Okay? It means the way in which we should study this process. So the answer to this is, so the adjective white, this I have taken from Simon Higgins' book because he has written it quite well there. So adjective white is used in the sense that, so this is I am quoting from the textbook, since that white light contains equal amounts of all frequencies within the visible band of electromagnetic radiation. I think this you may remember, we used to do an experiment where we used to place a prism and we used to see that if you are passing white light through it, all the 7 colors will come at it as an output. It means all the 7 colors somewhat uniformly mix and create the white color. Okay, so it contains contribution from all the possible visible band of electromagnetic radiation. That is what the meaning here is. That if at all in the time domain, this has contribution from all the frequency components. Okay, so that is why word white is associated with it. It means the adjective, maybe the person who first must have modeled it, so he picked this word from there. Okay, so this is one of the questions which I answered. Then the next thing is, okay, first is what is a proper definition or the classical way to define it. / classical way. Okay. So one is a strong sense white noise. Strong sense, it means a stronger definition. What is it? A process XT is strong sense white noise if XT is IIT. Now what is this? Let me write it down. With mean 0, and finite variance sigma square. Now, what is the meaning of it? IID simply means, I think you must know this, but I'm writing it for the sake of completion. That is independent and identically distributed. What do we mean by this strong sense? It means if I take any for any ti comma tj where I is not equal to j, x of ti and x of tj are independent. Now this is really very weird, okay? It means this is a very worst case of noise which adds to the system. Why worst case? Let us say at time t equal to 9 am you get the value as 2. Then you do not know at 9.01, okay, that is a 1 second later, what value you will get. That value can be -1 also, that value can be 10 also, that value. It means there is no correlation of 2 with that value. So it means even if I have some estimate of my signal at time t, that is 9 am, I cannot say that whether that estimate of mine would remain correct at 9.01. Because a completely different noise adds to it. Okay, so the two samples, that is two random variables, because we know for a random process, if I fix time so that I get a random variable, so these two random variables are completely independent. Secondly, expected value of x of ti square is some constant sigma square. It means it doesn't matter. Sorry, this is should be x square. Okay, that is variance. Okay, that is sigma square is independent of time, and expected value of x of ti is 0. This is may not be very much required. You can. It means that the two are independent of time. The two stats, the two moments are independent of time. Okay. So this is a white noise in a stronger sense. Now let us deal with white noise in a weak sense, which we generally use. So weak sense, white noise. That is what we have defined that day, which has a PST. This will also have a PST uniform, but this imposes the condition that the two random processes x of t and x of t are independent. In weak sense, we simply say they have to be uncorrelated. Okay, this is also called as second order or weak sense. Okay, white noise. Okay. So x of t is second order stationary with expected value of x of t is 0. Okay, that is independent of time, and covariance of x of t comma x of s. Suppose I take it two different times, that is equal to sigma square 0 for t equal to s and for t not equal to s. Okay, so this is a weak sense. So we have not said that x of t and x of s need to be independent. We have simply said that they need to be uncorrelated. So now one more important thing is that if the covariance is of this form, okay, and I have said that this is second order stationary, so I can take the Fourier transform of it to obtain the PST. Okay, so in this case, using the Wiener-Khinchin theorem, in this case, PST can be obtained by the Fourier transform of covariance. Okay. Now, what is this covariance? So, this covariance is nothing. If I need to write it in a shorter notation, this would be sigma square delta of t minus s. Okay. So if t minus s is 0, then it takes a value. If t minus is non-zero, it doesn't take value. If I take the Fourier transform of this, so I will end up with a PST of this sort. Okay. So basically, the definition which we used that day has a reverse engineering approach in order to understand this white word first. Okay. So that is what is happening. So that is, we have defined a weak sense white noise where we are simply saying that any two elements are uncorrelated and the mean is 0. It means the first and the second moment, basically we have written it to be a white sense stationary thing, no? Second order stationary, or you can say this is nothing but white sense stationarity. Means I don't know which book you will refer to, so you have interchange of words or notations at different places, but things have to be clear from the context if you are a very interested reader and you read things properly. Okay, so this is the definition. Now let us just simply write one small thing about it. What do you really intuitively mean by this? So for white noise, since Rx of tau is equal to 0 for tau not equal to 0, what does this really mean? Any two different samples, I have said it, but I'm not stating it. So any two different samples of white noise no matter how closely, this is important, no matter, let me write down, no matter how closely together they are in time, how closely together in time, they are taken are uncorrelated. That is the meaning. Okay. Now this comes the main point. Okay. If the white noise x of t is also Gaussian. Okay. Now comes that why do we assume that additive noise to be white Gaussian noise? Then the two samples are statistically independent. Okay. Why? Because in this scenario, when they are Gaussian, uncorrelated implies statistical independence as well. In a sense, now if Wn becomes a Wgn, that is white Gaussian noise, represents the ultimate in randomness. Basically, it becomes a noise in the strict sense, okay, or the strong sense, white Gaussian noise, okay, maintain randomness. Okay. So I think at this point we can close our session for today. Okay, if you have any doubt or any comment, then you can definitely talk to me. Otherwise, we will meet on Tuesday and we would start with the match filter. Then we have, I think, we do not have any further base to build. We will just simply use whatever preliminaries we have studied, and we will now design the receivers for the different modulation formats which we will be transmitting. Okay. So we're done for today.